Okay, I think we have enough data here. We'll proceed with this. I think we have spent sufficient amount on this exercise. What I'll do now is, although we have made some fake entries here, assume that all these people which are here, they are real and these are the endorsements they have made. So each of them has given you which all persons they would endorse or which all person they will recommend. So can anyone guess what we are going to do out of this data? No one? So we are going to build a network out of this data where everyone who is here in the key, everyone is a node and he or she is connected to with a directed edge to all the persons which they have endorsed. So actually we here in this particular case, since everybody has endorsed all 6 people, everyone has made the maximum number of endorsements. One thing which will happen with this network is every node will be having a degree of 6. Anyways, what we'll do is we'll analyze this network and I'll also show you one another network from one of the other FDPs which we conducted. So I'll take some time now to crunch this data to remove certain noise from here and bring it to the right format. Meanwhile, what we'll do is you can definitely keep watching my screen. I'll be doing some coding jugglery, which is, I think, straightforward. You need not worry about that. So at the end, I can share all my code with you and you can play around with that. So meanwhile, you can watch the screen and simultaneously think about what will be the properties of such a network which you see here. So we are going to make a graph out of it and think about what will be the properties of this graph. And you can use that to answer some of the questions here. So it's a small questionnaire for you. You can go here and try answering the questions here till the time I try to get this data into shape. I have got 5 responses so far. Okay. Um, I'll just stop it now and we'll proceed further. Okay. So here I have a R notebook and we'll do certain analysis on this data. So I have named our data as network.gml. Okay. So are there certain questions you would want to answer from this data? So I have certain set of questions and we'll answer them one by one. Meanwhile, if you think that there is something you would want to inquire from this data, let me know and we'll think about it. Hitesh, GML is a format in which you can store the networks. There are various ways of storing graphs, as we know. So one is adjacency matrix, adjacency list. GML is a specific way of storing a graph, and then you can port it across multiple languages like R and Python and use it. So my objective in this talk was not to exactly tell you all the coding behind it, but to tell you the characteristics of these networks. So let's first of all take a look at how our network looks like. So as you see in this figure here, this is the network all of us have created together. Rather, so this is the network here. Here, if you probably see, since most of the people have made 6 endorsements, I think the out degree will be 6 for most of the nodes. And in degree definitely will vary across different nodes. So in degree tells you how many people have endorsed you. Out degree tells you how many people you have endorsed. And you can see that despite the fact that many of the people haven't filled in entries, that is, every node didn't make an endorsement, still this graph looks very dense and it is connected. So what I'll probably do now is I'll show you this network, which has been collected from an FDP at NIT Jalandhar. And then we'll inquire some of the real world properties from there. This is the network we have. Okay, so whenever a network comes to us, so in our case, we have taken a network between the participants. So rather, whatever analysis we'll be doing now on, you can use it for any kind of network. It always need not be a network between people. So there are a lot of real world data which comes in the form of network. If you can design a network between the web pages on internet, you have a network between the neurons in your brain, you have protein-protein interaction networks, you have ecological networks, we have citation networks, or you can create your own data set. So whenever you want to study a new kind of network, so whatever properties we're looking for this network here will actually hold for all of those real world networks. So let's first look at how many nodes and how many edges are there in this network. Then we'll go further. So that is the very first thing anyone would like to know. So we see here that there are 86 nodes in this network and there are 398 edges. So can you tell me how many possible edges can be there over a network on 86 nodes. So we know that there can be 86 choose 2 number of edges. So in case it is a complete graph and we have very less number of edges from there. Actually, we have only 5% of the total possible edges, and even then our graph is connected. So out of every 100 possible edges, we have only 5. That is, for every 20 possible edges, we have just one edge in this network, and still this network is connected. So that is one of the very interesting properties of all the real world networks. So we know that our real world networks are sparse. There are not a whole lot of edges, and that's why we shift from adjacency metrics to other kind of representations like edge list and adjacency list, because they are sparse. But even when these networks are sparse, they are actually connected. So although we know that a network will be connected in n minus 1 edges in case it is a spanning tree, but that doesn't happen with the real world network. So any real world network will not be in the form of a tree. So tree is kind of a made up network. Here, if you talk about a real world network, so if a network has n nodes, we can actually prove that if you put log n number of edges randomly in this network, the network will be connected. So this is the actual real world network between people. I want all of you to think about what kind of questions can one ask on this network, and can they infer something useful from this data. So one of the things I would want to see in such a network is which person is the one who got the maximum number of endorsements. Yes, Hitesh, we are slowly coming there. So what is the main use of this network with respect to the data? So we had the data, we converted the data in the form of a network, and now we are trying to see what information this network can give us. So what all can we infer from here? So in the workshop, in the FDP, which we conducted, we had this graph. And one thing we would want to see is which person had the maximum number of endorsements. So it seems like that person would be liked by most of the people there. So in that case, one of the things which we use is in degree, which is one of the first idea which will come in anyone's mind. So in case this network was undirected, here it is directed, then it would tell us which person has the maximum number of friends. In this case, it will tell us which person was ranked the maximum. Can you think of something else? Do you think that in degree is sufficient to tell the importance of a person? So assume that there is an institute, there is person, he is endorsed by, let's say, some 10 BTech students. And there is another person, he is actually endorsed by the director and vice chancellor. So although the second person has an in degree of 2, which is less than the first person, but that second person might be more important because he is being endorsed by the important people. So this is, and this idea, which seems to be very simple, is actually used by the Google search engine. So do you know how Google search engine works? I had this experience yesterday. So somehow my browser search actually changed to some other search engine than Google, and I could see the difference between the two. So when you do a Google search, mostly whatever you are searching for looks in the very first and the second link. But you try some other search engine, that might not be the case. That's why Google search engine became so popular. What is that one idea which Google search engine use which is different from the others? So what do search engines actually do? How do they figure out which web pages are the most important? So you will definitely, you are going to do a text search. You will be using some NLPs to look at the synonyms. Samhita says find common search pattern. Okay. Madan says page ranks. Yes. So what do page rank actually do? So page rank says that you are going to rank the pages. But how do you actually rank those pages? What is the procedure behind that ranking? So which page comes at the top? Why is it at the top? Okay, by this same analogy I have given, Samhita says maximum in degree. Okay, this is any statistical method we can use. Okay. So here I'll take some time and I'll tell you how exactly this Google search engine works. In degree is one of the important measures. Principal is more important than a student. Yes, but in that case, we have the labels. So there is something out which might tell you this web page belongs to a principal and this web page belongs to a student. So you rank this one more. But that's not what exactly Google uses. Rather, it does not use any of the labels associated with pages. It uses the concept of a network and it looks at that network of web pages and then it figures out which is the most important web page. So like our own network here in this figure, so let me just enlarge it a little bit. So we have this network between all of us, right? Similarly, web pages have a network between them. So let's say this is a web page for node 41. So assume that each of us have a web page. All of us make some web pages, maybe during some FDP on website designing. And we have these links. And what these links tell us, so this 82, the web page corresponding to the person 82, it will have certain hyperlinks, which can take a person to some other web page. So 82 might have a hyperlink which can take you to this web page 38. It might have a hyperlink which will take you to the web page 18. So in this way, Google makes a graph, a directed graph between these web pages. Right? So you have this directed graph of web pages. Now you have to figure out which is the most important web page out of these, which is the second most important web page out of these, so that it can display us. How do you actually do that? So one idea is, okay, I look at the web page which has the maximum in degree. So I think, let's say this web page here, 51, it has almost an in degree of 12. Assuming that this is the highest in degree, Google might tell me that, okay, this is the web page which is the most important. But do you think that is fair? Can there be problem with this approach? So assume that I know that Google uses this algorithm because the algorithm of Google is open. Everyone knows what is the algorithm, and say we know that Google just look at which pages has this maximum number of incoming links. So what I'll do, I'll create a web page. I'll make 1,000 other random web pages, and all of them will start pointing to this one web page. Right? I'll give the hyperlink of this one web page in all of those 100 fake web pages. So that way I can increase the in degree of a particular web page, and that will create trouble for Google. Rather, assume that it is a Twitter network and the links here tells who follows whom, and you want to figure out which is the most important person on Twitter. So if you just look at in degree, so what I'll do is I'll create 1,000 Twitter accounts and I'll start following myself. So that way I'll become the most important Twitter user. So there seems to be some problem with this naive concept of only the degree. So to counteract this, there have been a number of centrality measures. So Google PageRank is one of them. I am now going to tell you how exactly Google PageRank works. And then I'll show you, I'll apply that on this network and we'll figure out which node here has the maximum Google PageRank. I'll explain PageRank with the help of two analogies. So I'll tell you two ways in which you can compute the Google page ranking in a simple way. And both of these techniques are actually the same. So you can mathematically prove, I am going to tell you two methods, method 1 and method 2. And you can mathematically prove that both of these methods are the same. So the first one is the gold coin distribution. Assume that this is the network between all of us, and now we are going to figure out which is the most important person here. So we know that most important person is not the one which has the maximum number of in degree, which has a maximum in degree. Most important person is the one which is being endorsed by the other important person. So assuming that Rajesh sir is one of the most important persons in this FDP, so probably the one person whom he is pointing is going to be important. Right? So what we are going to do is we are going to give all of these nodes some gold coins. So I'll give all of you, let's say, some 10 gold coins or 100 gold coins, let's say. I give all of you 100 gold coins. And what you will do, you will distribute your gold coins equally between all the people you endorse. So here, this 62 node here, it is endorsing node 85, 23, and 71. So if it has 100 gold coins, it will distribute almost 33 to 85, 33 to 23, 33 to 71. Other gold coin, maybe it can break it up into 3 pieces and give 1 to each. So 62 gives all of its gold coins to these 3 people. And every person does the same. So it's not that 62 will become empty. In this very same iteration, this node here, 59. So 59 is endorsing 62. 59 was also having 100 gold coins. It will also divide them, assuming it has a, let's say, out degree of 5. It will give 20 gold coins to 62, 20 to its other neighbor, so on and so forth. And every node will do this. So you distribute your gold coins to all of the people you endorse. So that is one iteration of the algorithm. After doing this, the same process is again repeated. Assume that after first iteration, this 62 gave all of its 100 gold coins and in return got some 80 gold coins from some of the people who endorsed 62. And again, we repeat the same process. So 62 will next divide 80 into 3 parts and give these gold coins to these 3 people. And these people, they will keep doing this, keep doing this, keep doing this. What do you think will happen at the end? Actually, this process will converge at the end. I'm not going into the mathematical derivation of that, but you can show that there will come a time when everyone will have this gold coin distribution in such a way that in the next iteration, when they again distributed, the distribution remains the same. So this distribution actually stabilizes. And where it stabilizes, that is the rank of every node. That is a value, page value of every node, and then you can rank them according to their values. So that was the method number 1. But if you look at this particular graph, can you tell me what is the problem with the algorithm I just told you? It has a serious drawback. So if I keep distributing gold coins in this network, for this particular network, I can tell you it won't stabilize. Why? So if you look at these nodes here, node number 23, 45, and this one node here, they do not endorse anyone and other people are endorsing them. So what will happen with time? These 3 nodes will actually end up collecting all the gold coins because they are not distributing it further to anyone else, but rest people are distributing it. So these people will end up having all the gold coins. So that is one thing which we have to tackle in Google page ranking, and there are ways to tackle it. So at every time you can evaporate some gold coins from everyone and distribute them equally across this network to ensure that there is no one person who ends up getting all the gold coins at the end. So that is one way. That was the method number 1. Method number 2. Method number 2 is based on random walk. So assuming that, let's say it's I go to a tourist place and these are different places there, and these are the roads which are connecting those places. I want to figure out which place is the most important or which place is at the center of this city. So what I can do is I just go to this place here, 71. I'll randomly go to any of its neighbors. So assume I came to 38. I'll again go to any random neighbors. I went to 40. So I'll keep roaming around this network. And while roaming around, whenever I'll come to a particular place, I'll increase its value by 1. So initially, every place will have a value 0. That is, it is not visited. And as soon as a place is visited once, you increase its visited value by 1. You keep roaming around, you keep increasing their visited values, you keep doing this, and at every step you can actually normalize these values, and this process will also converge. So the place which will be visited the most will be the one which will be having the highest page rank value. So this is how Google search engine works, utilizing this network between the web pages. So I can, in this network, I can actually comment all of this. And we can see here which nodes have the maximum degree. Actually, if we had a very nice graph between the participants, we could actually figure out which participant is the one in the center. So I can see here these are the nodes which are having the maximum degree, and these are the nodes which are having the maximum page rank. Okay. What else can we infer from this graph? So figuring out which is the central person is one thing. What else can we see? So I might want to see, if I have done it on a big set of participants, I might want to see whether the endorsements they made were genuine, or it was a kind of I rub your back, you rub my back kind of a phenomenon. So I endorse you, you endorse me, and we are done. Or is it sort of genuine? So for that, what we can look at is how many of these edges which we are having, they are bidirectional. So that we call reciprocity. And in that particular network, we were having a reciprocity of 0.6. So we could say it was sort of probably the participants knew each other beforehand, or they were friends. So if you do this exercise between the people who are friends, it is likely that friends are going to endorse each other. So which will result in an increase in this reciprocity. So what we'll do next is we'll convert this graph. So till now this graph was directed. So since this reciprocity is high, so we see some kind of friendship links there because people are endorsing each other. So what we can do is we can convert this graph in an undirected one, where if two people mutually endorse each other, we have a connection between them. Right? So I'm going to do that and show you the undirected version of this network here. So this was a directed graph. So this one over here. So this is the undirected version of this graph. So what you can observe from this graph is again what you observe in most of the real world networks. So here you can see that this graph is not connected. So if you look at the directed version of this graph, that version it was weakly connected, not strongly connected. And now if you look at the undirected version of this graph, it is disconnected. Although it is disconnected, you see a very interesting thing here. So yes, we have certain nodes which are not connected to anyone. We have this small component here. But do you see this big component here? Let me just change its layout. Do you see this one big component over here? This again you will see in most of the real world networks. Whether you take a Facebook graph or a Twitter graph, you will observe something like this. So the graph will definitely be disconnected because daily we have new profiles being made on Facebook who haven't yet added any friend. But if you look at the Facebook graph on a whole, there will be this one giant component, this one very big component, and this is true for most of the real world networks. So what generally we do is, generally whenever you do the analysis of these real world networks, you ignore all these small components and the analysis is kept confined to only this giant component. Okay, now what all can we study over this big giant component? So we have looked at if it was a network of web pages or if it was even a network between people, how we can figure out who is the most important person. We can look at the in degree, out degree, or in this undirected version, the degree of a person, which will tell how many friends a person have. Anything else? Is it all, or can we do something more with this network? Now assume you are the Facebook administrator and you are given all this data about Facebook, the network between the people. So what all kind of Facebook apps would you like to make? What all do you think can you do with this data as a Facebook administrator? Before that, let's even talk about some more properties of the node. So we have talked about degree, we have talked about parent centrality. So there can be some more ways in which these nodes can be important. So if you look at this graph here, what do you think will happen if I just delete this node from here, this 33rd node? So what if this person goes on some tour or some vacation? So do you see that this graph will actually then break in two parts? What if I remove this node here, 20? It will actually, I think, break this graph into multiple parts. So there are certain nodes here which are responsible for keeping this graph together. And if you delete some such nodes, so we call them cut vertices in the normal graph theory notation, this graph will become disconnected, right? So that is another kind of importance. You can weigh nodes based on this. What else? There is one more kind of importance you can weigh nodes based on. So if you look at this node, so let me look at this node. Let's say this node 21 over here. So this node has around 6 neighbors, and this node 20 here, it has slightly more neighbors than 21. Is there some difference between these two nodes? So if I look at the friends of this node 21 and the friends of this node 20 here. So if you look at the friends of this node 20, so 20 is friends with 71, 14, 33, 51 and 27. None of them are friends with each other. Right, so 20 is kind of a node whose friends are not friends with each other. But if you look at this node 21 here, so many of its friends are friends with each other. Does that have some implication? And one of the research have shown it. So this is actually called clustering coefficient, which tells you how many of your friends are friends with each other when you normalize it. Basically, what fraction of your friends are friends with each other. And it has been shown in a research that the teenage girls which have less value of this clustering coefficient, so mainly their friends are not friends with each other, are more prone to committing suicide. So even studying the structure of these networks help you make some sociological inferences. Okay. Do you think do you observe any other property in this graph over here? One of the very important topics in this field is community detection. So whenever you see a network of any organization or any school, any company, people will tend to be organized into communities. So there will be some people who will make their own group. There will be some people who will make their own groups, and there will be a few connections between these groups. So in this particular case, if you look at this network, so these nodes 27, 19, this part of the network, it seems like it's one group. If you look at this part of the network, it seems like other group, and this node 20 is somewhere responsible in binding these groups together. So we have certain algorithms called the community detection algorithms, which you can apply on this graph and figure out the communities in this graph. So let me just quickly show you this. Just give me a moment. Okay. So if you look over this graph here, it doesn't look very deep. Yes. So this graph over here, it shows the various communities in this network. Maybe if sometimes we could hold one more session, we can discuss about community detection. So these are certain things which we can do with all these networks. So if we are studying a social network, there are certain more things which are important. Let me just go to my slides. So these days, as all of us know, that this disease, corona, is spreading, and people are interested in studying, or it's even important to study how do diseases spread. So, do you think that these are only the diseases which spread from person to person? So again, whenever you want to study the spread of a disease or maybe some other phenomenon, maybe it's a video which is being shared on a social networking site. So how does this video spread from one person to other? If you look at all these spreading phenomena, they are heavily based on the structure of the social networks. The one I have just shown you. So if I'm studying the spreading of any particular disease, I can actually ignore all those isolated nodes and those nodes which are organized in small bunches and focus on that one giant component there and figure out which is that one node in the center of the network so that I can really vaccinate this node, because if I do not vaccinate this node, it will quickly spread the disease to all of the other nodes. So these are not just the diseases which spread from person to person in our social networks. There are a lot more things. So depression is one of them. And there is one very famous TED talk by Dr. Nicholas Christakis, who was once a hospice doctor at the University of Chicago. So hospice doctor is the one who is treating, not actually treating, looking after the patients with terminal illness. Basically, the patients are ultimately going to die. During this time, he was studying this widowhood effect in his lab. Do you know what widowhood effect is? Widowhood effect says that if your spouse dies, so your chances of death actually change, it increases. And in the case of males, if their spouse dies, their chances of death are 50% more as compared to when a spouse of a female dies. He was studying this widowhood effect in his lab. During this time, he was observing this pair of mother and daughter there. So there was this mother who was dying of dementia. She was being taken care of by her daughter. The daughter was exhausted of caring for her mother, and there was daughter's husband who was feeling bit scared of this because of his care towards his wife. And one day, Nicholas, he gets a call from the husband's friend who was feeling depressed because of what was happening to his friend. Do you see what is happening there? So if the people in your immediate family are depressed, it increases your chances of depression. And it's not just your immediate family, it's not just your immediate friends. If your friends are depressed, it also still increases your chances of depression. Maybe not that much, but it still has an impact. Similarly, even obesity is contagious like depression. In a particular study, it has been shown that if your friend is obese, your chances of becoming obese increases by 45%. If your friend's friend is obese, your chances of obesity increases by 25%. If your friend's friend is obese, still your chances of becoming obese increases by 12%. And it's only when you reach to a friend's friend that there is no correlation between your obesity, your body mass index, and their body mass index. It's not just that only negative things spread, even positive things like happiness spread. But yeah, not as fast as obesity. As you can see here, it's 15% on the first level, 10% on the second level, 6% on the third level. Anybody wants to speak anything? I hear some voice. There are certain more things which spread from people to people. Smoking. So if your friends smoke out of peer pressure, your chances of smoking also increase. The phenomenon of quitting smoking is also contagious. So if your friends stop smoking, your chances of smoking are less. Okay, do you think clapping is contagious? There is a very nice video based on this one. Maybe I'll give you a YouTube link at the end. You can go and watch it. The video is very interesting. So, what you will actually realize after watching this video, assume that you are attending a talk, offline talk, where everyone is present right there in front of you. And most of the times when people clap, it's mostly not because of each of them feels that the talk was extraordinary. People clap because a selected few audience starts clapping, and this phenomenon of clapping is also contagious. So when somebody is, let's say there are two people sitting, one on your left and one on your right, and they start clapping, you'll also have a peer pressure to clap. So that way, clapping is contagious. Phenomenon like voting and laughing are also contagious. So these are few things which sociology addresses, and specifically social networks also address them, and they try to study their spreading behavior. So be it diseases, be it information, or be it all this phenomenon here. Rather, you can refer to this work by Dr. Nicholas Christakis. They have collected around 30 to 35 years of people's data where they record everything. So they record the body mass index of people, how it is changing with time, their immediate connections, who is your father, who is your mother, who is your sibling, who is your friend, who is dying, who is getting born, and they represent every person with its BMI. So if a person is having a large BMI, he will be like as a big dot in the network. If a person has a small BMI, he will be a small dot in the network. And they show you this big animation over a period of over a 5-year period. Sorry, it's a 5-minute video for 30 years of time, and you can see how this obesity network changes. So you can actually search it on YouTube and you'll find that very beautiful animation. So these are a few things which spread on the network. So let me just end this talk by giving you a few pointers. So in case you are looking towards studying or modeling how do things spread in a network, it can be a disease or it can be an information. What are the challenges you will face and how you can overcome them? What kind of models you will actually use? So in case you plan to take it up as a research project or something. So the very first thing we have just talked about is the structure of the network. So if you're talking about information diffusion, assume that you make this so during this COVID time, you make, let's say you love dancing and you make this dancing video and you want this video to become viral on internet. What will you do? So assuming that it's not a very big Facebook network, but you know the network between your friends, right? So you know that if you share your video with a friend who is isolated, or a node having 0 degree, it's not going to go anywhere in the network. So can you look at this network between your friends and figure out which is that one most influential friend with whom if you will share your video, it will become viral? That is one thing. So the structure of these networks help us a great deal in doing that. Definitely, we couldn't talk much about the structure of the networks here, although we have looked at that there is one giant component, there is high clustering, different kind of nodes and things like that. Okay, now assume that you want to now model the spread of COVID-19 phenomenon. How will you do that? So this is one challenge which epidemiologists face every now and then. So assume that there is this disease spreading, contagious disease is spreading in your institute or let's say your city, and you want to model it. So one problem there which we face is the lack of the data. So definitely diseases also spread through networks. So if you want to visualize it as a complete phenomenon, what you will do is put every node, every person as a node in the network. So if I'm doing it for COVID-19, let's say, so I'll have this two-dimensional grid. Every person in this world, I will put that person as a node in this network. And if a person has a connection with any other person, so this connection can be very short-lived. It can be even just a 5-minute walk in an auto, or it can be a 3-minute flight. I should have a connection between those people, right? Assume that somehow I capture them. I lay down these nodes. I lay down all those connections. So I'm trying to make a model for this. And next, I should know that who infected whom, so that I know how this disease is spreading in the network. And then only then I can do something about it. But that is a tedious task. That is actually impossible. We do not have this network. This network changes so quickly. There are so many links. I cannot keep track of this, right? So, in the case of disease spreading, we do not have this network. We even don't know who infected whom. So, in the case of an information spreading, you can explicitly tell. So, if you share somebody's post, so it we know that who infected whom. But in case it is a disease, this subtle phenomenon is rather invisible. When I was in my sixth standard, the eye flu was spreading, and the three other people in my home, they were suffering from eye flu. The very next day, I also suffered from eye flu. But how do I know which is the actual person who infected me? There is no way to know, right? So this makes epidemiological model slightly challenging as compared to information diffusion, but there are ways out to deal with it. So sometimes people assume that since we do not have this data, you just assume that everybody is connected to everybody else. You make that assumption and you proceed forward. Or rather, this seems like too strict an assumption. Everyone cannot be connected to everyone else. So you fix a number. You say that, okay, one person is connected to some other 100 people in this network, and then you model it. So on and so forth. You have different kind of models. If you want to look further into it, I'll actually mention two models here, which are generally used in epidemiological models. So one are the compartmental models, and other is the branching model. So this was about the epidemic spreading. Now, if we talk about an information spreading, okay, not just information, let's say we are talking about the adoption of a product, right? So how do products spread from person to person? So why should I purchase an iPad, and which version iPad should I purchase? Which restaurant I should go? People never make these decisions on their own. So there is also a kind of influence there or a spreading there. Assume that you are going to this new city, and before going there, you have to choose which restaurant you will go. So we'll quickly go to some of the online website and look at various ratings of different restaurants, and based on that, we decide. So there are actually two things which happen to us when we have to make a decision. These are called the decision making models. So there are certain decisions which we make which are influenced by what is happening in the entire world. So assume I have to choose a restaurant here. So I'll actually go to, so it's not that I'll go to all my friends and I'll ask them which restaurant I should go to. Rather, I'll go to an online website and see it there, right? So such kind of behavior is called the herding behavior or the crowd psychology. So whenever you see a lot of people doing something, you also tend to do that thing. So these are called as herding models. I'll just write it down here, herding behavior. So in this herding behavior, there is actually no network at the back. So you can actually model them using your Bayes theorem. So using your Bayes theorem, you can actually model which product you should purchase next, which restaurant you should go to. You also use it in predicting whether an email which comes to you is spam or not. How do you identify that and stuff like that? Then there are certain decisions which you made based on your friends. So when you were in your BTech and you had to decide whether to attend a class or rather you would bunk the class, again, so for that you don't go to any online website and ask, right? In that case, you look at your friends, see what they are doing, and accordingly you decide. So assume that half of your friends are actually saying they want bunk, and half of them are saying they will bunk. What will you do in such cases? Right? So in such kind of things, we use the game theory models where you look at the payoffs. So what is the benefit I am getting if I bunk the lecture? What is the benefit if I am attending the lecture? How many friends are there who are bunking? How many friends are there who are attending? You mix all of these. So your brain mixes all of these. And then you take a decision, and you can actually model it as a nice game theory application. So if you have heard of this prisoner's dilemma, you might know it. Prisoner's dilemma is a very interesting puzzle. You should look at it. So these are four kind of models which are generally used for studying the spreading behavior on networks. I think that we are almost on time. we still have some 5 to 6 minutes. So I'm now open to questions. If you have any kind of questions, please ask me.
If anyone has questions, participants, if you have any question, please ask.
Sir, may I ask?
Yeah, ma'am, please.
Uh, Good morning, madam.
Hi, ma'am. Good morning.
Ma'am, I have a question. You talked about the page ranking in Google page, now, madam.
Yes, ma'am.
Can you just indicate which is the page ranking algorithm you are currently using?
So what I have discussed in my talk is a very basic version, but the fundamental concept which is used behind the page ranking algorithm. If you will look at it now, then yes, there are a lot of things used. So assume that you are searching about a particular institute. So definitely you will not be crawling the entire web for it. So there will be certain search queries which will be used. So maybe you will obtain around 500 pages which are related to that institute, and maybe you can then chart a network out of that and then use it. So which page rank is being currently used, I'll look into it and maybe I can share it on the WhatsApp link, because these things keep changing very dynamically.
Okay, madam.
Anybody else? Anybody else has questions? Otherwise, we will end the session. No questions? Okay, then thank you, ma'am. Thank you, Yati, ma'am. You have
Thank you.
presented very well. And
Thank
session
you
was
so
so
much.
interactive. It was very interactive. And we can
Thank
easily
you.
perceive that you have done a lot of work on data crunching and data analysis. And your slides shows this thing that you are too experienced in this world. So we are the
Thank you
journey
so
is
much,
very
Sujata.
beautiful, ma'am. For us, it was a new learning experience, and I hope all the participants will also gain something from this today's sessions, and the session which are going to be conducted on 12 o'clock, 12 noon. The session on 12 is also on the same topic, that is data crunching. We will continue this journey in the next session also. And I hope the ma'am's teammate will also light on this matter more. He also continue the session with this data crunching and his experience. Thank you, and thank you very much.
Thank
And
you.
I hope we will get the slides by email also, so that
Yes,
we
sure.
can participants, ma'am.
Sure. I'll share the slides. Rather, I'll also share this code. Maybe if someone wants to have a look at it, you can play around with this.
Yeah, please.
Yes. Okay.
Then thank you, ma'am. We will disperse for the tea break, and we will again meet at 12 o'clock. Thank you. Thank you very much.
This conference is no longer being recorded.